Alright, so these Jacobian. Jacob boy. So Jacobian of functions of several variables. Let u x comma y, that's let u and v be functions of two independent variables x and y. That's what we are saying. The Jacobian of u and v denoted by j u comma v all over x comma y, or partial u over u comma v all over partial x comma y is defined by, so the Jacobian of u and v denoted as this is defined by the determinants partial u over partial x, partial u over partial y, partial v, partial v over partial x, partial v over partial y. So your a11 is partial u over partial x, a12 is partial u over partial y, a21, I guess that's how we call it, a21 is partial v over partial x, a22 is partial v over partial y in a 2 by 2 matrix. Yes, so for this thing now, you're giving three functions u, v, and w. You're giving three distinct variables u, v, and w, and they are functions of three independent variables x, y, and z. The Jacobian of the function uv, or the Jacobian of uvw is denoted as this, and it is defined as in a 3 by 3 matrix. A11 is partial u over partial x, a12 partial u over partial y, a13 partial u over partial z, a21 partial v over partial x, a22 partial v over partial y, a23 partial v over partial z, a31 partial w over partial x, a32 partial w over partial y, a33 then partial w over partial z. Okay, so in general there's like a general expression for this. Just go through it. I hope it makes sense then. So what you need to know is that the one on top, I call it like a hack now to get it. The one on top, the first one will be the one on top. It will go through each of them. Then the second one will go through each of them. The third one will go through each of them. The last one will go through each of them. So when you're starting with u1, you have u1 over x1, u1 over x2, u1 over x3, and u1 over xn. The next line is u2, u2 over x1, u2, just like that. Then you have u3, then you have un. Makes sense, right? Very simple. This is like, this is not a 4 by 4 matrix, so this could be, okay, let's say this will start from 4 by 4 to as much as 8 by 8, 7 by 7, but I don't think anybody will give you that kind of long thing to do. So let's leave these properties aside. Yes, let's work with this. Alright, so example, you're given that x is equal to r cos theta. You see that question again. Y is equal to r sin theta. Find Jacobian of x comma y over r comma theta and Jacobian of r comma theta and x comma y. Solution: x is equal to r cos theta, y is equal to r sin theta. So you know how the Jacobian should be: x over r, x over theta, y over r, y over theta, just like partial. So now partial x over partial r, x is equal to r cos theta. Differentiate with respect to x. Sorry, differentiate with respect to r. This is going to be cos theta. So partial x over partial r is equal to cos theta. Then differentiate this with respect to r. Partial y over partial r is equal to sin theta. Yeah, then differentiate this with respect to theta. Partial x over partial theta is, you're differentiating this is going to be minus sine, so it's going to be minus r sine theta. Differentiate this with respect to theta is going to be r cos theta. Okay, so I had to split my note, but we'll take this column, then take this column. So Jacobian, now we've gotten this thing, the values we need in the matrix, the determinant now. So you know how you take determinant, this times this minus this times this. That's what you do. Minus and minus is plus. So we have arrow cos squared theta plus minus and minus plus arrow sine squared theta. Factorize, you have arrow brackets cos squared theta plus sine squared theta. What did they call it? I think it's a trigonometric rule. I don't know what you would call it, but it's something to take note of. Cos squared theta plus sine squared theta is 1. So arrow bracket 1 is equal to arrow. Just take note of this. It's going to come later, and the other ones too we need to take note of. And as you come along them, I guess we'll just pinpoint it. So let's go to the second Jacobian. We have to find Jacobian of arrow comma theta over x comma y. Now you have partial r over partial x, partial r over partial y, partial theta over partial x, partial theta over partial y. X is equal to arrow cos theta, y is equal to arrow sine theta. Now recall that we can't just work with this. Why? Because we have arrow here, we have arrow here, we have theta here, we have theta here. But so if you try to get arrow here, you'll be having different I don't know if you understand what I'm saying. So it won't work. We have to join them. Why did x and y own? Because x now was a differentiable function around theta. So x is a function of r, x is a function of theta. Y is also a function of r, and y is a function of theta. But here is separate. Here is separate. Is I don't know how I'll make you understand, but is in this form now. When we want to differentiate with respect to x, r is separate. It won't work this way. So we have to use Pythagoras theorem to merge it so that we can get a single function for x, y, and r, get a single function for theta, y, and x. So that's what we did from the last one. So I guess by looking at it, you remember. So by Pythagoras, x squared plus y squared is equal to r squared. Theta, opposite over hypotenuse. So tan theta is equal to y over x. Theta is equal to tan inverse of y over x. Now differentiating equation 1. This is equation 1. Differentiating equation 1 partially with respect to x will give you 2x equals to 2 arrow partial r over partial x. Make partial r over partial x subject to formula. Partial r over partial x is equal to 2x over 2 arrow. You have x over r equals to cos theta. Now differentiating equation 1 partially with respect to y. 2y is equal to 2r the r over dy. The r over dy is equal to 2y over 2 arrow minus, you have y over arrow. Recall that we said y over arrow. Okay, let's start with this. X over arrow is cos theta. Cos theta is equal to x over arrow, and sin theta is equal to y over arrow. So x over arrow, the r over dx is equal to x over arrow, that's cos theta. The r over dy is equal to y over arrow, that's sin theta. Now for theta equals to tan inverse of y over x, differentiating partially with respect to x gives, let's come over to this side of the book. Partial theta over partial x is equals to, we are differentiating theta equals to tan inverse of y over x. That's what we are differentiating. So differentiate with respect to tan inverse, 1 over 1 plus d square times differentiation of this with respect to x is minus y over x square. You open this up, you have y square x square. You collect like terms, sorry, you do the lowest common LCM, lowest common multiple, then you inverse it and multiply, you get to this point. Check other videos if you don't understand what I'm saying. You have x squared over x squared plus y squared. Or let me just explain what I just said now. You have 1 over 1 plus y over x squared. It's going to become 1 over 1 plus y squared over x squared. When you take the LCM, let me separate here. When you take the LCM, you're going to have 1 over The LCM is x squared. This is 1 over 1. So 1 into x squared times 1 is x squared. Plus x squared into x squared is 1. 1 times y squared is y squared. So this is what you have. So now let's bring out these two fractions. You have 1 divided by x squared plus y squared all over x squared. We want to change this division to multiplication, so we inverse this. So you have 1 over 1. This is also 1 over 1 times x squared over x squared plus y squared. Yes, so that's how we got this. That's how I got this, times minus y over x squared. So my this cancels out this, and you have minus y over x squared plus y squared. Alright, but you say but. Okay, there's a but here. X is equal to r cos theta and y is equal to r sin theta. X is equal to r cos theta and y is equal to r sin theta. It implies that partial. Okay, so we want to now substitute the values of y and x into this. So partial theta over partial x is equal to minus r sin theta minus times this minus r sin theta all over x squared, which is this square, y, which is this square. Now partial theta over partial x rather is equal to minus r sin theta all over r squared cos squared theta plus r squared sin squared theta. Partial theta over partial x is equal to minus r sin theta all over, take r square, factorize r square, and then you have cos squared theta plus sin squared theta. Recall cos squared theta plus sin squared theta is 1, so you have minus r sin theta all over r square. This cancels this. Partial theta over partial x is equal to minus sin theta all over r. Differentiating theta. Alright, so we've gotten our partial theta over partial x to be minus sin theta over r. Now we want to get partial theta over partial y, so we said differentiating theta equals to tan inverse of y over x partially with respect to y gives partial theta over partial y equals to the same thing we've done, but differentiation of y over x with respect to y is 1 over x. You inverse it just like I explained earlier, cancels out. You have x over this. Recall your x is r cos theta and your y is r sin theta. So you put them, substitute them, you simplify as best you can. So we factorize here, collect cos squared theta and sin squared theta. So you have r cos theta all over r square. R cancel r, you have cos theta over r. So the theta dx is minus sin theta over r. The theta dy is cos theta over r. Alright, so we are solving the Jacobian now. The Jacobian of r comma theta all over x comma y is the r over dx. You see, so the r over dx cos theta, the r over dy sin theta, the theta over dx minus sin theta over r, the theta over dy is cos theta over r. You take the determinant, so this times this minus this times this, so you have cos theta times cos theta over r minus sin theta times minus sin theta over r. We have cos squared theta over r plus minus and minus is going to give you plus, then sin theta times sin theta will give you sin squared theta over r. Take out 1 over r, you have 1 over r brackets cos squared theta plus sin squared theta equals to 1 over r times 1, and your answer is 1 over r. So now here's the property of Jacobian. Let f and g be two functions of x and y. Jacobian of f comma g all over x comma y times Jacobian of x comma y all over x comma g is equal to 1. Now we did a similar something. We did Jacobian of x comma y over r comma theta and Jacobian of r comma theta over x comma y. We said from the properties that when you inverse Jacobian and multiply it, you're going to get 1. That's what we did from our solving. Jacobian of x comma y arrow comma theta is arrow. Jacobian of arrow comma theta and x comma y is 1 over arrow. So when we multiply this, arrow you have arrow times 1 over arrow, and multiply, you're going to get 1. So this property is very much correct. Alright, so that's it for Jacobian.